Okay, this is about the relationship between the distance of the object from the surface of the spherical transparent body where we're going to have refraction and the position of where the point is going to focus. So we're not going to talk about the magnification at this point. We're just going to talk about the distance from the object to the surface and the surface to the image. So P is where the object is, P prime is where the image is. This is probably air, and this is something like glass in terms of material. So what happens is the light ray comes in. Well, there's two light rays. One that goes straight at a 0-degree angle of incidence to the interface, and it'll just go straight through. Now we need another point, a second point, to determine the point of focus. So what we do is we take this at some angle alpha with respect to the horizontal. It comes up here and it refracts. If you draw a line perpendicular to the surface, and a line perpendicular to the surface is a line from the center outward, because any line drawn from the center of a circle to its surface is going to be perpendicular to the surface, and then we extend that out. So here's our line perpendicular to the surface, so we have the angle between that line, the perpendicular line, and the actual incident ray. Then we have the refracted ray. Notice, because this coefficient of what do you call it? Coefficient is it coefficient? The index of refraction. The index of refraction, this is going to be less than that, so it's going to bend towards the line that's perpendicular to the surface of that point. Now, just to show you that's one point. Let's say we went to another point. How would things be different? Well, here again, this is the line that's perpendicular to it, so you'd have your light ray come in. And let's extend this thing out so that it goes out to there. So that's your radius. And so the light rays are going to come in like that, and then it's going to be bent. So if it went straight, it would just go like that, but it's bent towards the, and actually would be bent right towards the focal point again. Okay, so let's just get rid of those. We only need to worry about one point. But okay, so let's define some angles here. So this is theta sub A would be the angle of incidence, and theta sub B, which is the angle between this radial line and the ray of refraction, the refracted ray, is theta sub B. So we can relate these two using Snell's law. Now there are some other geometric relationships. This angle here between these two rays is alpha. The angle between the radius and the horizontal vector is phi, and the angle between the refracted ray and the horizontal is beta. The height from here, this point where the ray intersects the surface and the horizontal is h. What that is going to allow us to do is to make some right triangles. We define the distance from the image to the surface as s. We define the distance from the surface to the, pardon me, this is the object. From the object to the lens is s. The distance from the front of the lens to the image is s prime. And the distance from here to this perpendicular distance from this point of intersection is called h. That's h. That height is h, and the little offset is called delta. Now, in the textbook you have, it basically says that using some geometric relationships, blah blah blah. In this case, it turns out this applies under certain conditions, and we're going to assume that alpha and beta and consequently phi are small angles. And what that will allow us to do is at small angles, the sine of theta equals theta, the tangent of theta equals theta. And therefore, we can also say that the sine of theta equals tangent of theta. So this is all at small angles. Let's just see how small angle we're talking about. So let's open up my spreadsheet. And let me share that with you. So the angle, and then we'll have the sine of theta and the tangent of theta. Start with 0. And then we have, let's use degrees. So let's go 0.1, 0.2. So these are degrees. The functions, sine and tangent, are in radians. So, okay, so there's 24 degrees. So let's go back here. And so we'll do equals the sine of the angle. We need to convert that to radians. So we're going to multiply by pi and divide by 180. And for the tangent, same kind of thing. Equals the tangent of the angle in degrees, multiply by pi, divided by 180. We get into radians. So let's copy that down. And okay, so what have I done wrong here? Say that equals the sine of, actually what we need to do is also multiply these by what we actually need to do is insert. So we need to have the angle in radians. So that's the angle in degrees. So we're going to say equals the angle in degrees times pi divided by 180. Okay. Now we're going to rewrite that as just the sine of B2. And this will be equal to the tangent of B2. Okay. So 0, they're all 0. Okay, now we're going to copy that down. Okay, so there we go. So you can see here at small angles, this is the angle, this is sine, this is theta. So, less than 1 degree. You go to 1 degree, and you're starting to see some difference. Not, it's in the 5th decimal. Let's go up to 10 degrees. So 10 degrees is 0.174 radians, and this is the sine, and this is the tangent. So you start to see some difference. It's still on the order of a couple of percent, I think. Let's just actually figure out what the percentage is. So to find the percent difference for sine, so say sine difference and tangent difference. So all you have to do is you take and we'll assume that we use the angle as the basis for the denominator. So we're going to take this minus that divided by that, divided by that times 100. Okay, there's something wrong. Oh, I think it's because it's 0, so they're all 0. Let's see if I copy this. Yeah, there we go. So you can see the percent differences. This is 0% difference. So as the angle approaches 0 degrees, which approaches 0 radians, you can see there's just a small percent difference. So at 10 degrees, we have about 0.2% difference. Actually, it's right here. It's about 0.5%. 0.5% less. So it's pretty close. Okay, so those are the assumptions we're going to make for small angles. Now, let's see what observations we can make. So we have that this angle here, remember from geometry that this is an exterior angle. So let me just draw a line. I'll take it off in a minute, but this line, this exterior angle is equal to the sum of the two interior angles. So we can say that alpha is equal to theta, well actually we can say that theta sub A equals alpha plus, and we're going with this line, so it's going to be plus phi. And you can do the same thing over here for this triangle. So what we're looking at is, let me draw the triangle for you to emphasize it. We're looking at this triangle here, and there, and there. And so the exterior angle is phi, and the two interior angles, opposite interior angles, are going to be theta sub b and beta. Okay, so let's remove those. So the second angle relationship we have is that phi, this angle, is equal to theta sub b plus beta. Okay. We also know that from the law of refraction that N1 sine of theta sub A equals N2 sine of theta sub B. So this is the perpendicular from the center through the surface is going to be perpendicular to the surface. The line between the perpendicular and the angle, the ray of incidence, is theta sub A, and the angle between the ray and the radius is theta sub B. Okay, so we know that. Also, we can say that the tangents of these three angles, alpha, beta, and phi, are going to be related. These are going to be related to this height. So this is the opposite side. If we draw a triangle, so the triangle we're going to look at first is this one. That's a right triangle. So what you can see, so I'm going to write that this over here. You can say the tangent of alpha is equal to the opposite, which is h, divided by the adjacent, which is going to be s to here, and then you got delta plus delta. Okay, let me delete those parts of the triangle now. Okay, the second triangle that we're looking at is involving beta. So that's going to be here, and then it's going to be that, and it's going to be that. Okay, so from that we can say that the tangent of beta is, again, the opposite side, which is h. The adjacent side is going to be s prime minus delta. So this distance from here to here is s prime. This distance is delta, so the remainder is s prime minus delta. And then you have the tangent of phi equals something. So let me erase these again. So it's the same height is still involved, but you're going to have it all the way up to here and to there. Okay, so what distance is that? That's s prime, and or you can say it is equal to, oh, I'm doing the wrong one. I just did that one, sorry. So what I'm doing is this triangle down to there. So there we go. Okay, so that's it. That's out. That's phi. So we have, this is the radius, and that's delta. So this distance here is r minus delta. The opposite side is still h. So it's going to be h over r minus delta. Okay, so that's that. Let's erase those again. Okay, now what we're going to do is we are going to assume over here, assume the sine of theta equals theta. That's true for small angles. So we're going to let this equation will just become n1 theta sub a is equal to n2 times theta sub b. And if you combine this with this one up here, you can see what I can do is for theta, so I can solve for theta sub a here. Theta sub a is, well, it's already solved for it. And this one, theta sub b is equal to phi minus beta. And make sure I'm doing this the right way. Yeah, okay. They're actually doing it in 2 steps. We can do it in 1. So now I'm going to take, let me just take these 2 here and copy those. Never can figure out why it doesn't copy. Okay. So if we plug those into here, we'll get n1 times alpha plus phi is equal to n2 times phi minus beta. And if we multiply everything out, we'll have n1 phi plus n1 alpha. n1 alpha plus n1 phi is equal to n2 phi minus n2 beta. So now we're going to subtract things here. And so I'm going to move this over there and move that over there. So I'll have n1 alpha plus n2 beta is equal to n2 phi minus n1 phi, and then you can factor out the phi, so you get phi times n2 minus n1. Okay, now another thing that we can do is that so it turns out that if we approximate, so okay, so let's put a box around that. We need that later. The tangent of alpha, if alpha is small, then the tangent of alpha equals alpha, and delta can't be neglected. Okay, and so if we look at the tangent of alpha, so the tangent of alpha equals h over s plus delta just becomes alpha, because the tangent of alpha equals alpha is equal to h over s. So we drop the delta part. So what I'm going to do is I'm just going to rewrite those 3. So we get alpha is equal to h over s. We can say beta is equal to h over s prime, and we can say that phi is equal to h over r. Okay, so those 3 things. And then as a final substitution, we're going to substitute these 3 into there. So I'll have n1 times alpha. Alpha is equal to h over s plus n2 times beta, but beta is equal to h over s prime. And that's equal to phi, but phi is h over s times h, or n2 minus n1. That can look like an h for a while there. Okay. So n2 minus n1. You see we have a common factor of h, so we can cancel those out, and they become 1. So we get n1 and not h. We just end up with n1 over s plus N2 over S prime is equal to N2 minus N1 over R. How did I get R? Because I didn't write this down right, so I should need to change this to R. H over R. Okay, so that's the terminology that's used in another textbook that had a nice picture in the derivation. In our book, you'll see that it says, so our text, using their terminology, you have N1 over P plus N2 over Q is equal to N2 minus N1 over R. And where P is the object distance, it's distance from the center line of the lens, center point of the lens to the object, and Q is the image distance. That is the convention that we use in our book. R is the radius of the lens. Lens radius. And of course N1 and N2 are the index of refraction. So we'll do a separate one on the magnification question.